Well, hi everybody, and also welcome to my talk at this very, very nice conference. I'm Dietmar Wohlbauer. I'm currently a postdoc in Boston with Julie Einberg, and thanks to the organizer for inviting me to talk here. And I will talk about neural sensitivity to electric stimuli in cochlear implants. And if you have any questions throughout the talk, you can just scan the QR code on the page. I mostly included in most pages, so like you can just send me an email and ask in the end of the presentation. Um, for those who for those of you who don't know what a cochlear implant is, this is a perfect representation of an implant, a very realistic one. Anyway, when we stimulate a cochlear implant electrically, we get an electric activation that might look like this is a spread of excitation or a neural activation along the electrode array. And what you can see, the activation is not very distinct to a certain region. So the problem is the current spreads out and we don't know yet exactly what's happening. So where is this current going? How large is the region? And how is the anatomy actually influencing this activation? So we need to understand the neural sensitivity of electric stimulation in the cochlea. And just before I start, I want to introduce a few terms like neural sensitivity, like how neurons react to electric stimulation, or the electrode neuron interface, which is the interface between electrode and the neural region, and also the quality, which reflects the fidelity of information transfer, which is very important to see or to understand what the electrode neuron interface actually shows or the differences we see. So to start, neural density in cochlear implantation is when we can basically stimulate a certain neural region and the neural region reacts differently. So in this case, we have certain electrodes stimulating at different places along the cochlea and creating an activation which might look like this. Of course, the spiral ganglion neurons, they don't move in reality, but you know what I mean. And we can also have some neural dead regions. Basically, it could be a difference in severity of dead neurons. Basically, in this case, we have less activation, of course, when we stimulate along the cochlea, but in the most severe case, we have this dead region where we don't get any activity. So basically, we stimulate that region and we don't get anything in response. So in reality, in the clinic, we would increase the stimulation currents and then we increase until we get an activation, which is not optimal because we get a broader spread of excitation, a higher current, higher thresholds in our case, which is something we don't particularly want. Then electrode location, of course, also has an influence. If we have a different distance between the neural regions we actually stimulate, then we get a broad spreads as well with high currents. And of course, this all goes hand in hand. In hearing loss and implantation, we have dead regions, we have reduced regions of like activity and also different electrode locations. And why do we need to understand these differences a bit more than we do now is because cochlear implant people do not perform the same as normal hearing people. And there's a large performance gap, which we need to understand or identify where it's coming from. And when we understood it, we can improve signal transmission on the pre and post processing side, for example, with different signal coding or also on the clinical side to understand, oh, maybe we identify a region that has actually no response to electric stimulation or a weak response. Do we understand? Do we need to stimulate this region? Can we deactivate this region? Can we compensate with different methods to stimulate this region? And also, the holy grail in electric stimulation or in cochlear implant stimulation is the individualized approach. So we can improve performance for the individual itself, which is basically not solvable in a general way. So when we understand every single individual, we can increase performance in the most optimal way. And of course, in the long term, improve performance. So the challenge is now to identify the right measures. Certain measures have claimed to be sensitive to the neural activity, for example, psychophysical tuning curves or the multi-pulse integration in the temporal domain. But I will talk about perceptual focus thresholds and the ECAP, the electrically evoked compound action potential, and specifically the amplitude we can extract from these measures. So when we combine those measures, we can possibly explain a little bit better or more effectively how regions react to electric stimulation. What is the perceptual focus threshold? We record these thresholds basically in a very similar way than in a clinical routine where we want to identify the threshold of the patient, but it has a different method which is not yet introduced. So hopefully I can make some advertising for this. But so we create a electrode quadruple which stimulates in basically a current sweeping uh, method the more distinct neural regions. So instead of having a very broad spread, we have this phase inverted edging electrodes activated to narrow the electric field to a more specific neural region. And then when we sweep through the electrode array, then we get a focused representation of the neural activity. So how does this look when we create a profile? Here in blue, you can see a sweep in one direction through the electrode array, and in orange we can see a sweep in the other direction. And then when we do this multiple times, we can average out a focus threshold profile that you see in black. You see there's lots of variation in this profile, so compared to a monopolar threshold, it shows you a more, or in theory, it shows you a better representation of the more distinct region along the cochlear implant, respective a different neural activity. The second method we're using is an objective method called electrically evoked compound action potential, or ECAP. This is recorded in a standard forward masking method. We have 4 frames of stimulation where we have to combine those frames in a very we have to record those frames, and then we have to subtract the ECAP response from those frames with this smart formula. What is it doing? We record the evoked compound action potential that you can see here on the right. We activate a certain region, and from the very low spontaneous activity, we can increase this activity on in this region of the electrode by stimulating with stronger and stronger currents. And then you see this orange curve, it grows with stronger current, and then we can extract the amplitude from N to B amplitude or peak. So there we get these two measures, these two infos, and for the ECAP, it looks very similar to the focus threshold profile because it's a profile, but we record it at maximum loudness instead of at threshold, and then you can record an ECAP on every electrode, of course, and it results in a profile that might look like this with different strengths of amplitudes or different ECAP strengths for a strong one that might look like this here, and a very weak one that might look like this. And of course, we can then combine these two profiles, which we're just gonna talk about from now on. The relationship of those ECAP and focus threshold profiles should be explained. For example, with a hypothesis like a high focus threshold corresponds to a low ECAP response, which in general explains a poor electron neuron interface. That's our hypothesis one. Here is the ECAP threshold profile in orange now, instead of rainbow colors, and here you see the focus threshold profile overlaid and converted to a dB. And you can directly see a negative correlation, and when we calculate this, it definitely follows our hypothesis, which is a great outcome for those one subjects, for this one subject. Then you have another profile to show you that there's some variability across people. This ECA profile possibly looks very similar, but the focus threshold profile is in general just flat. So of course we don't get a negative correlation with this, but we identified that in those subjects we often have a region that follows our hypothesis of negative relationship. And if we could identify this partial negative correlation, then we could potentially find a negative correlationship which follows our hypothesis again. But to also show you that there's a complete different subject group, especially this one subject, we can have a positive correlation as well, which doesn't follow our relationship or our hypothesis at all, which is, of course, nothing we particularly want to see, but you will see this is a very special case. I I built or I grouped those subjects in 3 categories. And to show you when we record this across all our subjects with extremely high variability, then we get these two groups of negative relationships and positive relationships. And just to show you how strong the negative correlation is, we can see that here are subjects from group one. We have a negative correlationship, which is significant and borderline significant, so very close. And this one subject as positive correlationship, I just showed you before. So you can already see that there is some um, that's a trend of more negative relationships instead of positive ones, which we want to see. Then, if we do partial correlations, we already identify a few more people that have a negative relationship. So this is much stronger than the positive correlation. In general, when we create a model with all the data, we can already see this. We can also see this negative correlation, and which basically uh, is what we expect and what can also be pretty nicely explained. However, to show you that it's really important to group the subjects and only look into the negative correlations due to the high variabilities, we can strengthen our outcome pretty much more when we ignore the positive relationships that are quite weak. And we wanted to look into a different relation, namely the input versus the output of the ECAP, only the objective measure. So does a high input current relate to a high ECAP as well, or the other way around, which would explain a poor neural interface, an electron neural interface. So there was a recent study which introduced a failure index, which is basically a ratio between input current and maximum ECAP amplitude. And they performed a study in animals where they lesioned the cochlea, micro-lesioned the cochlea to degenerate the nerve in this area, and then they recorded ECAPs as we do it. So basically, they increased the stimulation current here on the x-axis until they found the maximum current where the ECAP doesn't grow much more, and then they compared this input versus output relationship. This was a non-lesioned subject or animal. On the right side, you see a lesioned subject, and when you do the same, you can see that the current still increases while the maximum ECAP is still decreased. When we calculate the failure index, you see high failure indexes stand for um, a bad ENI. So the outcome is, so to say, should explain the lesioned part of the cochlea. Throughout all subjects or all animals, you can see that the failure indexes are in generally pretty high compared to the control animals. So how can we use this information in our study to identify bad regions across the whole electrode array? Of course, we can do this same comparison. Instead of only one failure index, we can record it or calculate it across the whole array. And what we find when we do a median split, as the original animal study did, we find poor electrodes and good electrodes, which we can also divide in the same way as the animal study did. The good point is when we look into the subjects where we had the partial correlation, only the upper electrode showed like what we saw in the threshold, we can perform the same and we can identify directly with the input-output relationship how these electrodes perform, even good or bad. And when we look into the focus threshold in comparison to this, we can already see this relationship as well, which is pretty much consistent throughout all our subjects. So when we do this, we can also compare those groups like in the original study. And the good thing is we get a high significant difference between high and low failure indexes without normalization and with basically taking into account the high variability across subjects. This is an ongoing analysis, so we are pretty happy about this, but there of course there have to be some more steps to uh, identify if this measure is really consistent. For now, it is. However, so in conclusion, to finish for today, we have the focus threshold profile, which can identify the differences, as well as the ECAP recording, which can identify poor and good neural regions. Then the failure index captures it in one measure, which is pretty much nice. And then we have the high variability, which of course has to be considered in any case with cochlear implant subjects. The best outcome we might get with combining those measures, which we just performing now, with basically putting all these measures in one bigger model and find the combination and the outcome. And also, what can we use this in the future for? Possibly for computational models to improve the outcome based on real human data. So what are the next steps? Of course, we don't know anything about the anatomy yet, or we don't consider them yet, that yet. So we have to look into imaging data, and we could possibly create uh, some more outcome measures that explain the anatomy and our findings based on the objective measures. And then we can also, or what we do is look into spread of excitation, which is just another ECAP metric. And so we can possibly identify more relationships between the failure index and the ECAP, the objective ECAP outcome. Well, thank you so much. This is the end of my presentation, and I'm happy to take any questions, either now or per email. Thank you.